Live streaming is on.
I'm gonna mute myself.
Live streaming is on.
Okay, thank you, Dan. I'm gonna go get started. I want to welcome everyone to the January 2022 General Meeting of the Baton Rouge Astronomical Society. Our speaker this evening is going to be Merrill Hess, and he's going to be talking about the Earth-Sun relationships and what goes along with it. So without too much further ado, I'm going to introduce Merrill. Merrill?
If you don't mind, I'm going to take this off so you can hear what I'm saying. Otherwise, it'll be muffled. Okay, can we get the PowerPoint started?
Yeah,
Right. Oh. This is actually, I just took the slides off the wall and modified them. So it's just a nice sunset. No green flash in this picture.
That should work. You can flip slides.
Yeah, working on that.
All right.
Okay. Sorry about that.
It's just a.
Did you do that or did you?
Yeah, I can. I think I can scroll slides.
Okay, yeah. All right.
If you can't scroll, just let me know and I'll scroll.
Well, I did it there, unless that was you. Okay, I think we got it now. All right. The point of this presentation is that someone expressed an interest recently about solar storms and their effect upon the Earth and their significance to our lives. So that's the gist of this talk. There's a leading up to that topic and then tying some things together. But first, I thought it would be good to do some basic introductory things about the sun, the way it behaves, what causes its behavior, and why that affects or creates solar storms, and how it affects us. So, some basic anatomy. What we see is, let's see, this part right here. This surface that we see, what we might call the surface, is actually the first visible layer of the atmosphere of the sun. We call that the photosphere, and that's the part that we see. And other types of filters that filter out the majority of the sunlight, let certain wavelengths come through. We can see certain details. For example, all of these features that we see in the photosphere and on the edges of it. The H alpha filter, like we have here, is a common type that will show these things. Koi, you have one, and a few other couple members of our club has one that's fascinating to use. But when we look at these things, people say, oh, these are features, but we don't know what to call them. Of course, everybody knows what a sunspot looks like. Right there with the blue lines pointing to each one. Those are cooler regions of the photosphere. That's why they look darker. As opposed to being 6,000 degrees centigrade, it might be 4,500. But still, that's cool comparatively to what we're accustomed to. And then we have on the edges, you can see the things that look like flames out on the edges. Like down here at the lower left, we call those prominences. And those are lit up, I suppose you could say, gases that follow magnetic field lines projecting from the surface of the sun. And whenever we see those from above, they look dark, what we call filaments. So these long, dark lines that we see are, just separated in various places. Those are filaments. Those are actually prominences that we're seeing from above, looking down on them. So if they were out on the edge of the limb, you would see them projecting out from the edge, like these other prominences. And sometimes you can get what they call the detached prominence. You really can't see it well on this slide, it's pretty down. But where they're not connected to the limb of the sun. We'll get into that in a little bit. And then there's these bright areas called plages, which are pretty much what they are, bright areas with a lot of energy. Of course, the sun is immensely huge. Looking at the scale of these sunsets, the Earth could fit inside that smallest one right there. And the larger one, is probably closer to the planet. I don't know, one of the larger planets for sure. But the scale is immense.
Do you having trouble moving the slide?
Yeah.
Before you move on.
Alright.
Yeah.
I've always heard, of course, that the sunspots are cooler spots on the sun.
Yeah.
And prominence has been cooler associated with sunspot that would pass through by the dark, right?
Yeah.
Now, what about the white areas? Like,
They're more
those
energetic.
hotter spots?
They're more energetic. They're emitting more energy. The other parts, they're also emitting energy, but they're spread out more, and they're emitting energy so fast that they cool down quicker. The other parts are, I don't know what you can say the difference is, but I guess there's more energy being fed into the plages, the brighter areas. Whereas the other ones are dissipating more energy. It's subtle, but anyway, this is just a different view, a more three-dimensional view, to give you an idea of just how complex all of these systems are.
Yeah,
Yeah. So the batteries are good?
no, the batteries are good. All right, you move that.
Okay, there we go. And more anatomy. You've always heard that the sun is a nuclear furnace, right? The core of it is where nuclear fusion is occurring. Most of the sun is plasma, atoms that are stripped of various parts of it so that they're electrically charged. Of course, right here in the core is where the nuclear fusion comes on. And there's a large region, what we call the radiated zone. We're not completely knowledgeable about the structure of all of that because it's just so deep. We don't know how deep it goes and what all the different layers are. And then you've got this convective zone where there's more like a climate, I guess you could say, where you've got lines of magnetic force that move around. Okay, can we go back? Well, yeah, I mean, that kind of gives it an idea. The convective zone, you saw that when you got that circulation. There we go. And then the photosphere, which of course is the part we see. And then we have the chromosphere, which is a thin layer, maybe about 10,000 miles deep, that surrounds the photosphere. And then the outer part of the atmosphere is called the corona, and that can extend out millions of miles into space, depending on circumstances. Anyway, we can go on. But just to show that there's a lot of layers that let's see if I can keep on. A lot of trouble with these slides.
Yeah, I need to. I think it's the extra camera is just adding an extra layer of complexity. I'm not sure why.
Well, anyway, like you see this layer of convection. You can see in this breakout image where hot gases are flowing upward to to the surface, and then going down and circulating back again. And this circulation of material from the inner core to the outer core could take 10,000 years or so. So you know, a photon of light can take that long to get from the inner core of the sun to the outer surface before it's ejected out into space. And we could see any small parts of it. And so you've got layers of, I guess you could say, weather within the sun, where you've got layers that rotate at different speeds. One, like layers of an onion or layers of a shell, where an inner layer would rotate at one speed, outer layer will rotate at a different speed, and then the outer layer will rotate at a different speed. And then within each one of those shells, you have lateral zones, I guess you could say latitudinal zones, that rotate at different speeds. So that when you look at, say, the photograph of Jupiter, you see the cloud belts. Well, those are different weather systems at different latitudes that rotate around the planet at different speeds, and that's why they striate the belts. Well, the same kind of thing happens not only from inside to outside of the sun, but also latitudinally as well. And so you have a very, very complex system with a lot of energy being created simply from, I guess, lack of a better term, is the friction of one layer moving against the other. Okay, so we're going to forward one. All right, and we don't really need to stop there because we know, I think we know enough about sunspots. And there we go. That's over that. We
Pass this. So I think I can.
There we go. Yeah, that's just a different view of the same thing. What we call convection cells. And you notice the granular look that you see on the photosphere. It kind of looks like popcorn or boiling water. And that's kind of the same effect that it has, where when you boil water, heat convects from the bottom to the top and then back down again as it cools. The same thing happens in the sun. So the hot gases rise up within these cells in the middle parts, right here, the white parts, and then cool off when they reach the top, and then drop back down into the lower layers of the atmosphere on the outer edges, which is the darker edges, cooler, therefore darker. Okay, and each one of these is very large. You know, most people say that the average convection cell is about the size of the state of Texas. So if you can get an idea of what that means when you look at the surface of the sun. Okay, keep going. All right, and of course, just like the Earth, it has a magnetic north and south pole. And this is where our talk starts taking a turn, because this is where all the crazy dynamics start to occur. The Earth is pretty stable. You know, our magnetic pole wanders pretty good. It's been wandering a lot the last 10 or 15 years. But, you know, for the most part, it maintains that same configuration with the lobes and the lines of magnetic force going from the north to the south pole. In one and out the other. And the sun does the same thing. But the magnetic field is tightly connected to the material in the sun. And so as the material starts to move around, the magnetic field gets pulled and stretched along with that material as it starts to move a bit. And they get twisted like that. And that's getting to an extreme point where, you know, the balls get ready. We'll talk about that later. But here's a good example of what happened. And I've got a little video I can show at the end, just a little short clip, maybe 15 seconds long, to kind of illustrate this a little bit. We can show you what happens. But basically, okay, just like the Earth, you know, you have up at the upper left, the lines of magnetic force go out, and you come back down, and you go out, and come back down. And there's everything's nice and hunky-dory, right? But what happens is, like I said, the layers of the atmosphere of the sun rotate at different speeds. And as they rotate at different speeds, that material, that lines of magnetic force can pull along with that material. And so one part's moving slower, the other part's moving faster, and it starts stretching those lines out. You know, as the material outstrips or outruns the other material. And what happens is that begins to coil up quickly because the rotation rates are significant enough that over time it pulls that a lot of those magnetic field lines along with them and start to wrap them up. And then it gets to the point where they, instead of going more horizontal or vertical, they become more horizontal, or they become twisted like over the right. And just, you know, since magnetism and electricity are interconnected with each other, just like with a electrical current, if you bring a lot of current, you know, down a wire, but then you bring those two wires close to each other, and the current's strong enough, instead of going along the wire, it'll jump across from one wire to the other over the gap. Well, the same thing happens here with these magnetic fields. And you get things like sunspots that come up from the surface, and if they come up high enough and have enough energy, they'll short circuit going across the middle, and they'll pop off and fly off into space, carrying the material with them. That's one form of the solar flare. Okay. And of course, you see this is a footprint of a sunspot. They come in pairs, have a north pole and a south pole, because what this is lines of magnetic force coming out of the surface and above the photosphere and then back into the photosphere. It doesn't travel like this, you know, like you think, oh, it comes out like a stream and then comes out like that. No, it doesn't. What it does is it comes out like this, so that it kind of goes out like that. You know, instead of going like a dart, you know, like you're taking water out the hose, it's like the hose arcs up and then breaks up. Okay. Go on. All right, and here's another example of what happens. It just gets extreme and extreme until what happens is, you know, it's just a different, we get a different look at the same process where, you know, for example, these two lines that used to be more vertical come together in the middle and then pop out and might become a sunspot right in that area. Okay, go on.
Hold on one second.
There's a experiment of sorts, a demonstration showing what happens if you use a rubber band. Maybe you've heard of it.
Mhm.
You take a rubber band, put it between your fingers, and start twisting it into a knot. And when the knot gets enough tension on it, like the magnetic field does, it will break.
Yeah.
Release all that energy from it.
Yeah.
They're very similar, even though they're different materials.
Oh, yeah. That's a good illustration. I don't know if you heard it with the line, but Craig said you can do an experiment with twisting a rubber band and twist it and twist it and twist it until it reaches a tension point where it's got to release that energy and the rubber band pops. And that's kind of an analogy of what happens, because there's a tremendous amount of energy built up in all of these sunspots and these bands of magnetic force that are associated with them. This is to illustrate something called a coronal hole. And you can see the dark spots in the photosphere. And this is taken in, I think, iron, maybe wavelength, if I'm not mistaken. And which reveals the coronal holes. And what this is just an area that's less energetic than the rest of the sun. So there's less energy being poured out of these areas. But they're rich for feeding the solar wind. Go ahead. And of course, you've seen all of this. What's nice about this is you can see the structure of the corona, and you can see how it's this nice symmetrical structure to its atmosphere. And actually, the sun looks very calm in that one. I don't know if you can notice it, but if you look closely enough at the moon, you can see features on the moon. Some of them are in craters there. but that's just to show how large the corona is compared to this thing. Everybody's heard of solar cycles, I'm pretty sure. Those relate to the sunspot cycles when we have active and less active sunspots. But what it really indicates is the progression of the twisting of its magnetic field to the point where the poles actually flip from north becomes south and south becomes north. And that happens over a roughly 11-year cycle and a 22-year cycle to complete the reversal again. And it's not exactly that 11-year, but it's roughly. And so what happens though is that at the beginning of the cycle, after the poles are flipped, the sun is relatively calm. But when it rotates enough to where the magnetic field lines start to become disrupted and start warping again, you start getting sunspots occur. Generally at the lower latitudes, or closer to the north and the southern poles. But as the sunspot cycle continues, they become more tightly clustered around the middle latitudes, and you'll see like a belt of sunspots at the upper latitudes, and as time goes by, those belts of sunspots will move closer to the inner latitudes. And sometimes it's clear enough to where you can photograph the sun, and you can actually see a line at these latitudes where these sunspots occur. And of course, this shows the cycles over a period of time and the intensity of the sunspot activity at each one of those cycles. Right now, we've been in a very, very quiet period for over 20 years. And we're just starting to become active again. And here's a good example of how it starts off relatively calm, and as time goes by, the cycle of the sunspots become more active until you get that very active series of sunspots at the latitudes closer to the equator. And that's when it gets to that point, it's getting close to the time when the poles are going to flip. And of course, there is a prominence, a huge ridge-like prominence that, of course, the Earth is there to scale, give you an idea of how large these are. This is not a solar flare. Solar flares can occur with these, but this is really just a prominence, where you got material arcing up along these lines of magnetic force, and that's what this is illustrating. It's like, you see, it looks like it's all fire, right? Well, it's not really. This is just hot gases that sort of become illuminated whenever these lines of magnetic force extend out into space. And material can't flow along them. And this is another phenomenon called a coronal mass ejection. And this is the largest explosion that can occur in our solar system. This is where as many as 10 billion tons of material can blow off of the sun in a very, very short period of time, in a matter of a few hours. And but you can have smaller ones and larger ones, different amounts. But you think that this is actually fairly common, and you think a billion tons or 10 billion tons of materials in a short period of time, blown off by each one of these, and you think about the age of the sun and how much more time the sun has to live, another few billion years, and you think that much material can blow off so quickly. How massive truly is the sun? How much material is there that it can blow off that much material and still have that longer lifespan? But these are the ones that, yes?
What time do the astronauts have and something like that?
Well, it varies. They can, depending upon the strength and the speed, the power, they can reach the Earth in a few hours or a few days. So that's the vulnerability that an astronaut has is, if something happens that we're not expecting, how much time do they have to prepare to protect themselves? And, fortunately, we have some measures in place to improve the odds with that. One of the simplest things is simply to turn the vehicle away from those oncoming particles so that they're more shielded. How much good that does, that's a different story. As it is, airline pilots can get a nice heavy dosage, like a good hard X-ray, if it's powerful enough if they're in flight. But solar flare is shorter, sudden, and bright. You can think of it like a shotgun blast. This is more like cannon fire. It's larger and more spread out and more powerful. And they can occur at the same time, but not necessarily.
I know that NASA was very concerned during the Apollo missions that we would get unexpected very large flares. And I don't remember, I think if it was bad enough, there's a possibility the astronauts might not have made it back.
Yeah, Greg brought up a point that, during the Apollo missions, there was some concern about the protection of the safety of the astronauts if something like this occurred. And, there's really not a lot they can do, depending on where they are. If they're on the surface of the moon, well, I mean, what are they going to do, get a lunar module? That's not really real protection. And the command module had limited protection.
Just as a side note, they were so worried about it, that's one of the reasons, there's this module they want to put in orbit, I think maybe it's L2,
Yeah,
or L1, or whatever it is, it's
pretty far away.
between Earth and the moon. They want to put a module there as a receiving station for anybody going to the moon. And it has extra insulation on it. And I think the theory goes that they can get to that module, they're going to maybe able to survive a really bad solar flare.
Yeah.
At least that's what they hope they can.
Yeah, except that to go to one of the L points, it's much farther than the moons. Okay, yeah, and of course, radiation is always an issue. I mean, that's why they try to time things to go through the weaker parts of the Van Allen belt when they went to the moon, so they didn't have to spend much time in the belts and reducing the explosion. And of course, these are just some headlines. These are actual headlines from newspapers and articles about, what the concerns are about if a solar storm hit the Earth. One of the materials from one of these events, a solar flare or coronal mass ejection, if it was projected out into space in a way that our Earth would run into those particles as they got projected out into space. So those billions of tons of electrically charged particles. Now, by the time they go out into space, they're not billions of tons by the time they reach Earth, but they're significant enough that they can carry a heavy electromagnetic charge and affect a lot of things in our modern technological systems. And, pilots and astronauts, they happen to be up there. I found this interesting. This is something I didn't know until recently when I was phoning up on this again, that airline pilots exposed to heavy solar radiation are at greater risk of cataracts, and the female flight crews experienced higher rates of miscarriages. Now, I don't know the details of that. I don't know if that means that if they are pregnant at the time they're exposed or if it happens afterwards. I couldn't find any details on that part. I just, that one little blurb. So that's something we're going to have to dig into a little bit to see if I can learn more about that. But that's interesting, I thought. And this one right here, in August of 1972. At that time, there were still some magnetically triggered sea mines in existence, and some of them were set off during that. I think it was a coronal mass ejection in that one that induced electrical currents into the ocean, and there were enough to discharge some of these mines. I don't know how many. It wasn't that many, but it was enough to cause a concern. Communication systems. Of course, what happens when you've got electromagnetic material, what happens when you have an electrical field, it can induce electricity. And electricity can create a magnetic field. They're interrelated to each other. So when you've got this electromagnetic particles flying up in the sun in intense levels, they can induce electrical currents into communication systems, into satellites. And we have had some damage to some satellites in the past that had some damage to circuits because they got a surge, electrical surge, whenever they were exposed to the solar storm. And I don't know if I have a slide of this, but I have a real short video again. What happens is we have, the Earth has a magnetic field, right? That magnetic field protects us from almost all the solar and those particles that hit us. But what happens during a solar storm, when it's powerful enough, is it can put pressure on that magnetic field and push it back closer to the Earth. And push it back far enough to where some of those satellites that are within the magnetic field and protected by it are now exposed to full space without a magnetic field to protect them. And they're fully exposed to the electromagnetic particles in these solar storms, and they can cause some damage. One of the ways to protect those instruments is to turn them, reorient them to where they have a smaller exposure. In other words, instead of standing broadside, like, arms spread out, you stand sideways to where there's less of the satellite that can be hit by these particles. It can help a little bit. Or they can turn the systems off, and because there's no current running through the system at that time, there's less chance that it'll get overcharged. It doesn't remove the chance, but it lessens it. GPS systems, they can be knocked out of whack so that they're not as accurate. And I read that, the modern GPS systems, they can be several yards of error. Well, okay, you might say, nothing, that's no big deal. What if you're driving a self-driving car? And suddenly it can't get the GPS readings from the satellite, and it's off by several yards. That can make a serious difference when you're driving, your safety of that vehicle. Also, guidance systems, airplanes, for example, cruise missiles. A few yards, down the range might not make a difference. A few yards at launch can make a huge difference because it's got a long time for that vector to go off, where if there's a few yards of error at the beginning. And electrical grids. And this is something that is probably the most serious concern for most of us, is that they can knock out electrical systems. And we've had a couple of those incidences up in the past. Probably remember March of 1989 when the Quebec power grid dropped down. And about 6 million people lost power for about 9 hours. In parts of the northeast U.S. as well, that were on that same network. And it created some scary times and some chaos for a while. And that was followed by a coronal mass ejection, a very, very powerful one, that was strong enough that it burned out the electrical transformers at the power generation station. And say, well, how can that happen? Well, what happens is, you say earlier, you've got electrical current, you've got a magnetic field, you've got a magnetic field, you've got electrical current. So when you have a solar storm that is powerful enough that it can reach into our atmosphere, and those electromagnetically charged particles fall past power lines, what happens is it induces a current into those power lines. And you've got an electrical grid spread all across the nation. Every one of those things is a conductor that allows electricity to be induced into those power lines and fed back into the transforming station. It creates an overcharge, a surge, and it blows out the transformers. Now that was a very, very serious issue at that time, because at that time, and even up into the 2000s, we had some very strong concerns about what happens if that happens over a nationwide or half the hemisphere, especially. Well, transformers aren't something you just go, oh, put the new one in and get it back on. No, they're built separately. They're all custom made. Hardly any two are alike. And they're manufactured as you need them. So if one burns out, you have to wait till, you know, you don't have one on hand, you've got to wait till a new one is built.
Up to 6 month lead time.
Yeah, yeah, he said up to 6 month lead time. But if you've got 200 of them knocked out across the country, that could be a couple of years before you get them back online. What do you do in the meantime? You're without power for 2 years? Remember this hurricane that just passed us. I don't know if you were affected, but you know, where I live, we were right in the eye of the storm. We were out of power for 22 days. And it made me think about this because you shift into a different lifestyle. And I had a home generator, a gas power generator, so I had to keep putting gas in every day. Decide what I was going to run, what I wasn't. And after 21 days, you develop a new habit, right? So by the 27th day, we had developed a new lifestyle adjusted to that new mode of living. And so that's what would happen to an entire nation. And so imagine, you know, you can't get gasoline, you can't get groceries because, you know, you can't get gasoline to fuel the trucks. And you don't have any communications. We were without internet for over 2 months. And no telephone, we had cell service hardly, almost. You know, it was very spotty. So we were flying blind for the first several weeks. You know, even though we're right here, you know, 30 miles away from Baton Rouge. And so you imagine that on a much larger scale, and imagine what kind of an impact that can have on your lifestyle and society. It wouldn't be fun. So that's why Homeland Security started taking this issue very, very seriously about 20 years ago, and started developing some protocols and methods to overcome some of these problems. Okay, come back. Just showing what happens, just giving an illustration of what happens whenever these billions of tons of super hot gases and charged particles are blown toward the Earth. And that would just, you know, the Earth is only about 10,000 miles in diameter. That's only a tiny region of space. And you just imagine how much material is flying out in all the other directions. And so one thing, of course, is you get is increased aurora, northern and southern lights, you know, in every campus. And I don't remember, we had a near miss back in 2001, where a large-scale coronal mass ejection just missed the Earth. But a lot of the particles came into the atmosphere, and some of you might have seen the aurora in this area at that time. I don't know if you did or not. The people in Texas saw it clearly, and people over toward Covington and Slidell saw it. I was never able to see it because I wasn't at quite the right location. But people 15 to 20 miles to the east of me saw some faint lights. And this is something that's we were talking about earlier, geomagnetically induced currents. And that's where currents are induced into the power lines because the electrical fields that are increased are moving around them. And also through the Earth itself and even through the oceans. So you can have currents collecting in the salt water. You know, the salt water is conductive. And it can move into the land masses and into these power systems from the oceans. Also, what else do you have down here on the bottom of the oceans? Connecting things. You've got pipelines and communication cables. You know, the transatlantic cable, right? Those things can absorb and get induced currents and bring them into the land masses. And this is just a graph that shows different types of effects. I think we've covered most of these already. Astronaut radiation, radiation damage from the satellites, solar cell and materials degeneration. That's something we haven't touched on. These magnetic currents can induce electrical currents, and of course they can increase corrosive effects on certain materials, especially metals, certain metals, and that can lend toward fatigue enough to where engineers, bridge engineers, for example, railroad engineers, have to take this into account to a certain degree, not a great degree, but a certain degree, enough to where they have to factor it into calculations for metal fatigue of the time. and of course, crewing passengers and airplanes, Aurora. And of course, communication, signal scintillation. I think we've all experienced that before, where you get signals broken up either on your radio, like your car radio, or in your cell phone. You get signals breaking up because of that. People with satellite internet service. And this is something I found interesting. I haven't had a chance to dig into. Decreased directional drilling accuracy. Any idea why? I can't think of any myself unless it affects the instrumentation.
It's how they give commands, because the directional, they drill down and they have to put like a wedge down in the bottom there, and the drill comes and hits the wedge and curves it out. That does the directional stuff.
Yeah.
And if they're off, like for GPS or something like this, if they're off just a little bit, when they do that, it's not gonna know exactly where they want it. Because it's gotta have it off somewhere.
Okay. And of course, this is an oil pipeline going across the surface. And of course, these have grounding cables all along the way, because they can receive electrical charges just from being there, from the atmosphere. And also from the air, whenever the air changes and you've got lightning in the area. And of course, if it gets a lightning strike, you want to ground that. But all of those things also affect the brittleness of the materials, and it has a corrosive effect on the materials. So that has to be monitored. And also, this can have a charge induced into it and send a charge down the line to the processing plant or collection storage tanks or whatever. So that can have some discharge risk from that. And this is back in 1989. We talked about in March 1989, the Quebec event that knocked out the power for the 6 million people. This is just within a 15-minute period or so, the aurora from the top left to the lower right, how fast it spread, to show how fast that material spread across the northern part of the northern hemisphere. Because right here you see it's well up into the lower middle part of Alaska is the lowest point. And down here, it's down around Iowa. So it spread that fast in just very, very less than half an hour. And so we have a large amount in a very quick period of time. So you have this intense burst very quickly. And it doesn't have enough time to dissipate as if it was spread out over a longer period of time. And this is the result. This is one of the power transformers, what it did to it. It just fried the thing, blew it out. And you can see by the person standing next to it, the scale of this thing and what damage it did.
I've seen one that blew up. I've seen it.
Mm-hmm. Like this?
No, that's burnt. I've seen one that literally blew up.
Exploded, yeah.
And it's filled with oil. All the oil that spills out, it's got to all be dug out and everything else like that. It's hazardous material.
Yeah. It's mostly mineral oil, right?
I don't remember exactly what type of oil it is, but I do know the one I saw, they had to dig 6 foot down for a whole area all around it and get rid of all that because of contamination.
Okay, so here are some solutions that will be utilized and still being further developed as well, because we have a long way to go. Less conducive materials, less conductive materials, materials that don't allow electricity to be induced into them as easily. That's difficult and expensive, so it's how much of that's going to occur, I don't know. And also more surge protection. That's a much easier thing to do, putting more circuit breakers along the lines, so that if you have an event that starts inducing current into a line somewhere, it goes to a certain point and it stops it. It takes it offline or it breaks it so that it doesn't allow it to collect and accumulate at a certain critical point down the line. And so that's a much more active and hands-on thing that's being done all the time. It's been done a lot already. A lot of it is in place, but a lot of it is still going on protect the system even more. The point is to decentralize the collection of energy so that it's spread out more along the grid. And that can take it easier in small locations that are much easier to repair or to bring back online. Another one is to simply take systems offline, just turn them off. A temporary power blackout. If you know that a power station is going to be affected, just disconnect it for a while. Let that energy dissipate and then bring it back online. It's inconvenient, but it saves people a lot from having another blackout that could be last weeks or months. And that gets down to, your personal stuff. People think, oh, well, all of our computers, all of our cell phones are going to lose all of that data, going to lose everything. That's not necessarily so. The reason is because that laptop right there, this little thing, it's a pretty small device. This energy is spread out over the whole Earth, right? Now, every square meter has an increased amount of radiation that it receives, but it's spread out over that entire meter. It's not enough of it that we see that this one little small object that is going to have much effect on it. So, your laptop, your cell phone, don't worry about them. They're not going to be a problem. But if you have it plugged into the wall socket, or if you have it plugged into your Ethernet or a telephone line or something where current could be induced and run through it and cause a power surge, yeah, it could be a problem there. So what you do is, if you know one is coming, simply unplug it. And you're okay. You should be okay.
So,
And if you really want to be paranoid, build a Faraday cage.
and
And then you get to the point where, okay, is my Faraday cage big enough that it's going to short out at a certain point?
I'll say, if you
Grounded
unplug
well
it,
enough.
the reason why you unplug is you don't just cut the power off and leave it plugged in,
Yeah.
because the surge can come across your power line, even though it's unplugged, and come into it that way.
Yeah.
That's why you have to literally unplug it.
Unplug it and move it a little farther away.
there's, you just told me that if I buy an electric car, I need to keep it unplugged.
Yeah, pretty much. Yeah, burn out the batteries. And better forecasting, of course. We're working on that all the time. Right now, we've probably got 24 different satellites that are specifically targeting the sun for observations of various wavelengths. And I know a lot of the photographs that I used to be missing from an old satellite called Solo that's been in operation probably 25 years now or so. And it's in orbit in a circle between us and the sun. It orbits a Lagrange point in space, which is really cool because it doesn't orbit an object, it orbits a point of gravitational equilibrium between us and the sun. And it keeps it aligned with the Earth in a plus relationship position-wise. Okay, and how do we monitor these things? We can go to a couple different websites, which I find very handy for laymen. This is probably the best one for laymen. It's spaceweather.com. And this goes from just the general knowledge for the public to highly in-depth. And you can go as deep with this as you want to. And every day, this is from yesterday, so was yesterday's space weather page. And it changes every day. Every day there's something new on this page. And one thing you get is the current weather conditions. It's just like you tune into Channel 9 or Channel 2 weather station. You get the current weather in space, right over here on the sidebar. And you can click on the links and go into further depth to get details on different parts. You get details on those sets of sunspots right there, on the prominences, on the output of solar radiation at the time. Quite a few different things that you can follow on a daily basis. And then as you scroll farther down, you'll get other up-to-date news. For example, Comet Leonard, that is still visible in some parts of the Earth. They're still putting updates about that one on there. So transient things that occur, meteor showers, things like that, we'll have information on. And then the next one, of course, is more detailed and a bit more for the, somebody a bit more knowledgeable is the NOAA, National Oceanic and Aeronautics Administration Space Weather Prediction Center, Atmospheric Administration. And of course, this has some very basic introductory things right here on the front page, but then farther down, it gets into, the more detailed areas. And so you can get some daily updates on that one too. And that's about it. Yes.
I read that thing every morning. I look at picture of the day, and find picture of the day, followed by looking at that to see what's going on in space. It does take a little bit of learning on some of the things they talk about, but most of it's pretty simple.
Yeah.
I don't think I have to use too much of my background in physics or chemistry, or in fact, practically none.
No.
But there is one thing that happened a while back on there. They were talking about the occurrence of events that could trigger major power outages. And the articles they selected seem to indicate that things like the Carrington Event actually may occur more often than we give it credit for.
Mm-hmm.
And for those who don't know what the Carrington Event is, you probably know, so I'll let you speak.
Yeah. Well, the Carrington Event was an 1859 August and September cusp event where a massive solar storm hit the Earth, and it's the most powerful one that we've recorded so far. And of course, we didn't have the same technologies we have nowadays. Back then, the most advanced technology was the telegraph. But it was enough to where it induced current into the telegraph system that it blew out some of them, and even set a couple of buildings on fire, and shocked a lot of people. They touched the telegraph and it shocked them, and they had to disconnect them. And so that one is one we use as a standard to measure things by. It's like the Hurricane Betsy of solar storms, that we compare everything to that event and see how powerful it is in comparison. We've had some that have come close. For example, back in 2012, we had a near miss that was almost that powerful, and it was very, very scary. And then we've had the one in 1989 we've already talked about, and there was another one that I didn't know about that occurred in 2017 while Hurricane Irma was hitting the Caribbean, and it had a strong effect on ham radios, which were being used in the emergency systems for the hurricane, and that had a pretty serious effect on what they were doing. And, that was news to me too. You can look it up. You can just do a web search on solar storms over time, and you can find some charts that list solar storms, and they actually occur fairly frequently. Different scales of intensity, but there've been about a dozen or so in the 20th century.
I read an extensive article on the Carrington, and one thing that fascinated me, the thing you mentioned, but the one that really got me was the two. One was the farmers, like the ranchers, get electrocuted by their fences.
Yeah.
And people could not work on the rails on railroad trains because they were getting knocked out, unconscious.
Yeah, I mean, the same thing, same concern is here. Railroad lines, they conduct electricity, so.
Did you mention the micro circuits and everything would be fried?
The fences, like you said, I've heard stories about, I think it was June Carter said that she used to go out to the fence and listen to the radio. Because it was, the fence itself was acting like a speaker. It was picking up the radio signals and transmitting them. And back at that time, they had some 1,000,000 megawatt radio stations in Mexico. And so they could transmit some pretty darn powerful radio signals.
I would not want to live in a city if the Carrington Event.
Yeah.
We'd have the least chances of
You kind of touched on something maybe John would know too, but what kind of unit numbers are we talking the globe that use those transformers? What was coming in? What do you think?
Well, those transformers like that, the big one like that, that's what's called a station transformer.
Yeah.
And to give you an idea, say River Bend, they have 3 of them out there for the whole output, which is over 1,000 megawatt, I believe. So 3 of them, so you say they're probably doing 300 to 400 megawatts of power running through those. When you get an induced voltage going back through it, it starts up with eddy currents and the material of the transformers and stuff, and it heats it up.
Yep.
When it gets hot enough, that's when the one that I saw blew up because of that, because it got too hot. And it oiled it like that. I don't really know the value, how much of a induced voltage it would take to do something like that. I could probably study it and find it, but right offhand, I don't know. I know the principles of how it did it and why it did it, but I don't know how much.
It probably varies by the system because, you know, you have a scale
Yeah.
to where, you know, it gets so large, it takes a lot more energy to, maybe in a logarithmic, I don't know, also semi-logarithmic.
Components of the transformer to the age, the oil to the age, there's just a lot of variables.
So just imagine how strong this stuff can be.
Yeah, I mean, you know, it may not be a large amount on any square meter, but when you collect it over, you know, hundreds of miles, you focus it, it'd be pretty intense. Scott, on the desktop, I got a couple of short videos up at the upper right. If you can reach those and click on them and play on it. I thought that people might like to see those. They're not on this, but yeah. Well, yeah, those. This just shows,
This is giving me an error with the playback.
oh, it doesn't like that file.
And this is the same thing with the files that you had embedded inside of your presentation with the tried to play, kept on giving me this
Oh,
error.
no, they didn't, I didn't need to play those anymore.
Okay. It looks like there's just something that's. It
That's
looks
fine.
like this laptop got scrubbed in the past couple of weeks, so I'm sure there's just like a clear deck or something like that that got trashed.
That's an MPEG file, anything should play that.
Yeah, should.
So,
I'd say the other site we're going to, like Space Builder is nice. If you just want to see what's going on in hydrogen alpha on the sun, a really quick one is the GONG hydrogen alpha, GONG, from the NSO. And they've got views from different telescopes around the world. And every once in a while you get a neat shot where a plane, I've seen a plane cut through, like multiple images of one plane passing through the shot. But if you want to see flares and the sunflux, because the reason why I look at it is I've got a hydrogen alpha scope. And so I'll look at this and say, well, is it worth getting my scope out and have a look? And if I got some flares or some prominences on there, okay, I'll set it up and have a look. If not, save my time and do something else.
Carol, remember you said you didn't see that aurora? If you could have been lucky enough to see a Carrington Event, besides having no power and great astronomy
Yeah.
you will have aurora over your head all the way to Cuba.
Yeah, it went down, the Carrington Aurora did go down to the Caribbean. So anyway.
Is that modified zero glasses we're using to predict solar storms?
Yeah.
thank you, Merrill.
John, this, I usually flip the YouTube video off and just leave it to the members. Would you like to do that?
Yeah, I would say so. Okay, we don't have things here more to go on. I just want to have a few, just